Now, hello everybody, and welcome from Graz for this month Astrophysical Colloquium. It's my pleasure to welcome our speaker, Professor Jamie Tayar from University of Florida, who will today give us an empirical picture about rotation in stars with some theoretical underpinning. Jamie obtained her PhD in 2018 from Ohio State University and secured a prestigious Hubble Fellowship, which took her to Hawaii, where she worked for 3 years. With January of 2022, she now became a professor at Florida University, where she's working and teaching. And thank you, Jamie, again for coming. It was always a pleasure to work with you, and I'm looking forward to your talk. The stage is yours.
Thank you. Okay, hopefully everybody can see my slides and hear me. Yes? All right, awesome. Then I'm excited to talk to you today a little bit about the evolution of stellar rotation, alone and together, inside and out, is what I've called it. And I love talking about stellar rotation because it's both important and useful, right? Rotation is one of the few initial properties of a star setting its evolution. You've got a mass, you've got a composition, you've got a rotation, and then everything else is physics. But in terms of that physics, right, rotation is also one of our largest uncertainties in how rotation should evolve, what that means for related processes, convection, mixing, magnetism. And so my hope is that we can use rotation as a tracer, as an empirical marker of what that physics is doing, and it'll allow us to infer something deeper about stars, their interiors, their evolution. Rotation can also be a very useful diagnostics. In many regimes, it correlates with hard to measure properties like age and magnetism, so you can use it as a diagnostic. And it can also tell you something about the history of the star, including its interactions with other bodies, stars, or giant planets. So in this talk, I'm going to try and convince you that we have detailed empirical data on what the evolution of stellar rotation looks like for stars relatively similar to our sun. I'm going to argue in this that binaries are not a negligible process. It's something like 10% of stars or more will interact with something over the course of their lifetimes. And that this evolution, this empirical rotational evolution, is telling us about a wide range of physical properties, including things like angular momentum loss and winds. It's how the physics of that loss is turning on or off, what the internal angular momentum transport is doing, how the interior of the star is talking to its envelope, and then, of course, the physics of tidal synchronization itself as these binaries interact. So to do that, I'm going to try and draw some analogies to our own sun, right? If you're more familiar with studying solar data, the sun is great because it's resolved spatially, and we have long baselines of almost continuous monitoring on year, decade, century timescales even. We also have the opportunity with our own sun to do things like in situ measurements of magnetic fields, of winds, of particles, and we can observe the sun in pretty much any wavelength that we find interesting, as somebody has taken data on. But there are some limitations to studying our own sun, and I think the stellar samples can provide kind of a complementary information on especially things like stellar rotation, right? Because if you're thinking in a stellar context, we have very large samples, which we can characterize well, so you can kind of draw a sequence. And so that means that you don't have to make an inference just on one star, and one data point is always a risky inference, but we can look at a sequence of stars like our sun and think about how they evolved from birth all the way through to death. We also have the advantage of looking at stars in this ensemble way, which means we can average over things like the inclinations of the stars, what's happening at the poles versus the equator. We can look at a range of initial conditions, whatever it was born with, whatever particular thing it started with, right? We can look at how the ensemble evolves, and so we're not dragged in any particular way by one outlying data point. And so when we're thinking about stellar rotation, right, there are kind of three main ways we measure stellar rotation rates empirically. So the first is using stellar rotation velocities. So if you take a high resolution spectrum of a star, you look at the individual spectral lines. Because part of the star is coming towards you, part is going away from you, you will see a rotational broadening of the lines that correlates with the rate of rotation, modulo the inclination angle in which you are viewing that star. And so either using individual lines or using an ensemble of spectral lines in a high resolution spectrum, you can infer what this v sin I, this rotation velocity, is. The second way we measure stellar rotation is to look at spots or active regions as they pass into and out of view in the star. Like our own sun, it will get brighter and fainter as the spots and active regions go around. And so over time, you can construct some sort of average rotation period of whatever active latitudes, whatever spots happen to be visible at that time. Now, of course, you have uncertainties, things like what are the active latitudes? Are there any active latitudes on that star today, right? If you go through a minimum, maybe you won't see as much activity. So there are, again, caveats in this method, but in many cases, it allows us to measure a reliable rotation period for the surface of the star. And then the final way we think about stellar rotation is to look at the power spectrum. And so if you're familiar with helioseismology, right, you've probably seen a power spectrum, a Fourier transform of either the photometry or spectroscopy of the sun. When you take that Fourier transform, you see at low frequencies the effects of the spots and rotation at kind of 25 days. At higher frequencies, you see the effects of convection and granulation. As you move to even higher frequencies, you'll see the effects of the solar oscillations. And when we observe other stars with space-based photometry, so this is high cadence, high precision work from missions like Kepler, or TESS, or Plato, which is one of the upcoming ESA missions, you're taking a photometric data point at millimag precision every few minutes. You get these same sorts of light curves of the stars, which the variation is not noise, but is in fact signal. And when you take the Fourier transform of that variation, you see a similar power spectrum, right? At high frequencies, you see the effects of instrumental noise. At lower frequencies, you see the effects of convection. And then in between, in many stars, you see the oscillations of that particular star. And if you zoom in on those oscillations, they tend to have a characteristic Gaussian shape, a power excess at some particular frequency, which we call the frequency of maximum power, and it correlates with the surface gravity of the star. If you then kind of squint at that power spectrum, you'll see kind of this characteristic picket fence of modes with some characteristic spacing that we refer to as the large frequency spacing, which happens to correlate with the mean density of the star. And so if you put that together, you have something that correlates with the mean density, you have something that correlates with the surface gravity, so you have an m over r cubed and an m over r squared, so you can put that together and get an independent estimate of the mass and radius of the star that's extremely precise. It's part of how we're able to do this kind of detailed characterization of sequences of stars, even in regimes where you can't just assume the evolutionary paths. However, if you zoom in on those oscillation frequencies, if you kind of stack each order on top of each other, you can construct what we call an Echelle diagram, where you basically have a frequency on the y-axis and a frequency modulo this characteristic spacing on the x-axis. When you do this, particular ridges will line up. You see the effects of the radial oscillation modes, you see the dipole oscillation modes, and you see the quadrupole modes. Now, if you're familiar with helioseismology, you often see many more higher order modes. In other stars, because they are spatially unresolved, it's very hard to detect. We usually only get up to about the dipole modes with the occasional L=3 mode. But even in these low order modes, you occasionally can pick out a mode that looks like it's either duplicated or triplicated. Basically, it's split with like a Doppler splitting or a Zeeman splitting. And this splitting, which Paul was actually one of the first people to observe directly in other stars, is able to tell you something about the rotation rate of the region where that mode is spending its time. So for stars more like the sun, less evolved stars, that tends to be the surface, the envelope of the star, and so you get an estimate of the envelope rotation. But as you move to more evolved stars where the gravity modes oscillating in the core can couple to the pressure modes oscillating near the surface, you can actually get an inference of what the rotation rate of the core of that star is using only the oscillations that you are able to measure at the surface. And so this gives you a way of inferring not only rotation rate, but sometimes something about the radial rotation profile, which can be very informative in terms of thinking about the physics of angular momentum, how it's being transported, how it's being moved between zones. Now in the sun, when you think about differential rotation, you don't only think about the radial differential rotation, but you also think about the latitudinal differential rotation on the surface of the star. On the surface of the sun. It turns out that in other stars, measuring that latitudinal differential rotation is extremely challenging. If you try to do it from the oscillation modes, there are a few cases where people have claimed, but it's not very many stars. If you try and think about using different spots at different active regions and how they should rotate at different frequencies if the star is differentially rotating, what we've found is that actually measuring that in a reliable way is extremely difficult to impossible. People have tried to do kind of theoretical studies of what you can measure, and so far there have been very few reliable constraints on the latitudinal differential rotation, particularly of more evolved stars. And so for this talk, I'm going to focus on the rotation, the average rotation rates, and then the radial differential rotation rates, rather than the latitudinal differential rotation. Okay, so then we're going to start thinking about stellar evolution, right? So how do stars start? Well, they're born in these giant molecular clouds of gas. If that cloud of gas has any initial rotation, initial magnetic field, as it collapses into a stellar core, that core will retain some of that angular momentum and so have some initial rotation rate. Since it is contracting, it will spin up. Part of that process, part of that regulation process, is it will often form some sort of disk around itself, which allows it to regulate that angular momentum in combination with winds and loss. And so these protoplanetary disks or circumstellar disks are starting to be imaged beautifully in data sets like ALMA. And so you can actually see the detailed structure of these disks around these young forming stars. But on the rotation side, what we've noticed is that that disk does indeed seem to help regulate the angular momentum of these stars. So if you look in a cluster, in a young cluster like the Orion Nebula cluster, for stars with rapid rotation, so small periods on the left side of this plot, particularly those that have disks tend to rotate at longer periods, whereas those without disks tend to spin faster. That's part of why we think these disks are helping to regulate the angular momentum budget. Basically, the star is in some way magnetically locked to its disk until that disk is starting to get dispersed. That dispersal, we can look at the disk fraction as a function of time. And that disk dispersal seems to happen over sort of 3 to 10 million year time scales, which means that that's about the amount of time you have to kind of set your initial angular momentum for the rest of the evolution of that star. That also means that you can go and look in young clusters. This is 1 million year old data from Rho of Yuki, looking at the rotation period now on the y-axis with fast on the bottom and slow on the top as a function of the spectral type or the color of the stars. I've tried to give you an approximate correspondence to the mass of the star on the top of this plot. Basically, you're saying, a 1 solar mass star, a 2 solar mass star, a half solar mass star. Looking at what the initial distribution of rotation rates that's kind of being frozen in during this disk process time. And then you can step forward in time to something a little bit older, maybe 8 million years. This is data from Upper SCO, where you can measure the rotation periods. And you can see, especially for those more massive stars, there's 1 and 2 solar mass stars where the disks have really started to dissipate. The contraction of the star as it contracts from a gas cloud towards the main sequence, where it can ignite its helium, or where it can ignite its hydrogen, for fusion, right? You see the rotation rate is starting to speed up. The stars are moving down on this plot to lowered periods and faster rotation. And then you can take kind of the next step to the next cluster at a much older age, say 125 million years in the Pleiades, and you can see that those kind of solar-ish stars have started to slow down again. And that's not because they're expanding here. That's something, some other physics has kicked in. And we think that's the physics of the stellar winds, right? The winds are carrying away mass, they're carrying away angular momentum, and so it's causing the stars to slow down over time. Now, if you're coming from a solar context, when you think about the solar wind, right, you probably think about that something that's relatively complex, right? It has multiple components. There's a fast wind, there's a slow wind. It's something that is not steady. It's time varying and spatially varying. It also varies with the solar cycle, the structure and morphology of the wind, the rates, and so on. And so when we talk about angular momentum loss in a stellar context, we're trying to simplify a little bit, right? Because in the solar wind, you can look at, with new missions like Solar Orbiter or Parker's Solar Probe, right? You can actually take in situ measurements of how that wind is carrying away mass and particles and angular momentum from our own sun. And it's got multiple components. It's got a fast wind and a slow wind. It looks right now like the slow wind tends to be doing most of the carrying away of the angular momentum in our own sun. And so when we think about what's happening in other stars, we kind of come up with a generic approximation for the average wind over some appropriate average. And we started out doing this in a very simple way. So this is a paper from Skumanich 1972, where they had data in a couple of clusters plus the sun and looked at what the rotation rates were. That's this middle line here labeled rot. As the star in solar-like objects of various different ages. And what they found was that the rotation was slowing over time as a function of time to twiddle the -1/2. And so people came up with various kind of simple assumptions of, okay, well, the rotation must slow down as a function of the rotation rate, and came up with a relatively simple parameterization so that we could make models of how the rotation rates of stars should slow down over time. But of course, those simple approximations are leaving out a lot of physics. And so more recently, people motivated by things like magnetohydrodynamic models and our own measurements in the sun have been trying to do something a little bit more sophisticated, where they say, okay, well, the average angular momentum loss from any star should be related to its rotation rate. It should be related to the Alfvén surface where the wind is being launched. It should be related to the rate of mass loss. It should be related to the balance between the rotation and the convective overturn timescale. And there's probably some factor that corresponds to a magnetic field geometry. And so people have worked through the math of that, looking at the torques of the star, looking at how the rotation loss should scale. And you can end up parameterizing this as a function of things like the radius of the star, the mass of the star, the luminosity of the star, the pressure at the photosphere, the convective overturn timescale, to give you something that's like a little bit more physical of how the average wind should scale with the properties of the star. And so I will come back to this later in the talk, trying to distinguish between these sort of simple formalisms and whether we need something more sophisticated like this. But the nice thing is, if we go back to these kind of pre-main sequence and young stars, that you can look at in various open clusters. And so these are going to be associations of stars of the same age and the same composition, but a variety of different masses, which correspond to different temperatures, how the rotation periods of those stars evolve over time. And you can kind of step through and say, okay, well, I can put in some sort of wind. Both of them are calibrated to more or less match this data, so it doesn't matter too much exactly what parameterization I choose, and I can look at how the rotation should evolve over time. The interesting thing is that when you do this, if you take data for stars of the same mass, but a variety of different ages using different clusters, what you find is you can't use just like a simple model of how the rotation should evolve over time. In fact, you can't just assume the whole star rotates as a solid body. And this is rotation rate here, rotation frequency. So fast is on the top and slow is on the bottom. So stars contract, spin up, and then the winds start to slow down the stars over time. If you use just a simple solid body model where you assume the whole star is strongly coupled, all rotates at the same rate radially, what you find is that you don't quite match the evolution. But you also don't match the evolution if you just assume some sort of simple hydrodynamic, relatively weak coupling between what's happening at the core and what's happening in that envelope that's driving a wind. And so you need some in-between hybrid model where you have some physical process that is transporting angular momentum, recoupling the core to its envelope over some particular timescale to match what we see observationally. And when you do this, you can compute what sort of time scales those stars should couple on. And it's sort of tens of millions of years, but probably strongly mass dependent. So lower mass stars taking longer to couple their cores to the envelopes, higher mass stars coupling faster. And so what that means is that if you look kind of overall at the pre-main sequence and early main sequence, what we see in rotation is that there are strong mass trends in what the rotational evolution is doing. We don't actually have a lot of data on what the metallicity trends look like because most of the open clusters near the sun are close to solar composition, which means it's hard to kind of do comparative studies very well. We note that stars are in binaries tend to rotate more rapidly. And then we have evolution that suggests that there is strong radial differential rotation in these stars with some mass-dependent timescale for coupling that core to the surface. So I'm going to pause here for 30 seconds and ask if there are any questions before I move on to kind of main sequence and later stars.
If there are any questions, please use the reaction item to raise your hand. Otherwise,
and you're going to have to call on people because I can't see the hands and watch everything
just
else.
one hand is up. Sasha, please go on.
Yeah, when you talked about the spin up for stars as they're contracting, you were showing a figure where there was basically a chain of points at the bottom. Is there any physical meaning behind this chain, or is this basically random?
This chain, you mean, or?
No, it was a bit before that. Yeah, yeah.
These. So the dotted line here is marking, I believe, the breakup velocity for stars of that particular mass at that particular age, given some estimate of what their radii should be. So you should not see anything below this line in terms of rotation.
Okay. Thank you.
And the blue X's are likely pulsators, which is why they kind of don't quite match what you would expect here.
There's a second question, but I keep an eye on the clock. I would say if it's urgent for the understanding, Philip, please state it. Otherwise, more general questions I would recommend to have in the end where we have enough time and people can leave them. But if you have a question, okay.
All right.
All right.
Sounds good. Then we will move on into the main sequence itself. So when we start thinking about main sequence stars, we're particularly interested in this case for stars that are close to what we call the Kraft break. This is around 6250, where you start transitioning from having a strong surface convection zone to a weak or disappearing convection zone near your surface, and having a radiative surface essentially. And that's because the convection zone at the surface we think is intimately linked to driving the sorts of dynamos and the magnetic field structures that are allowing you to lose the significant angular momentum in a wind. And so you can look at a distribution of stars, and this is work from Ellis Avalon, who is a graduate student in Hawaii that I worked with, looking at, as a function of temperature, as a function of stellar mass, what the actual rotation rates of these stars are, and how that is related to their properties. And so in this plot, you can immediately see we've drawn kind of a red line where the craft break ought to be, that there is a sharp transition between rapidly rotating hot stars, which tend to have radiative envelopes at periods of a few days in yellow, to lower mass stars where there's a transition to kind of slower rotation, 10 days, 20 days in green and blue as these stars evolve. And that's more consistent with what we see in our own sun, a rotation rate of something like 25 days. And so you can see that there are strong mass trends in this data. But given that this is a sample of field stars, we also have a little bit of a range of metallicity, so compositions. And we can look and see if there's any composition dependence in the sorts of distributions of rotation rates that we measure. And in this case, we don't see any significant trends. Now, there have been suggestions in other work that there should be trends or that there are trends. It could be some combination of the samples we're looking at. We're not sure yet. But at the very least, we don't see strong metallicity trends in what the distribution of rotation periods are. We do, however, notice strong trends in the rotation distribution with binarity. So in this plot, we're looking at the rotation periods modulo the sin I factor, because we're converting this from rotation velocities with fast on the left and slow on the right. We see presumably single stars in blue rotating relatively more slowly on average. The orange represents wide binaries, and the green represents tight binaries. And you'll notice that between wide binaries and single stars, we don't see any real strong difference in the distribution of rotation rates. But for tight binaries, where tides may be important or disk dispersal at early ages, we see on average much faster rotation. And so that's something to keep in mind when you're thinking about how the ensemble should evolve. And then, of course, you'll ask, what are the interiors of these sun-like stars, these approximately sun-like stars doing? So in the sun, people can use the helioseismic inversions to try and get an estimate of what the rotation profile of the solar interior looks like. We see strong latitudinal differential rotation in the surface convection zone. But as we move into the radiative regions, people have suggested that it's relatively flat in rotation. It's not too far away from a solid body. Now, there have been suggestions that perhaps the deep core of the sun rotates significantly faster. That's particularly hard to measure because the gravity modes in the core don't couple well to the pressure modes we see at the surface. And so those measurements are extremely challenging and rarely and basically not possible directly in stars, solar-like stars other than our sun. And so we have to make kind of a more indirect inference about what the interior rotation profile looks like for these stars. And one of the ways we have tried to do that is to use tight binaries. So if you imagine a binary star, right, as it gets close, the star starts to tidally synchronize until the orbital period is close to the rotation period, or the orbital period matches the rotation period. However, if your star is strongly differentially rotating radially, then the rotation period that matches the orbital period should be some average rotation period of the full star. And if there's something enforcing differential rotation, then that average period is going to be somewhere in the interior of the star. And that means that the period at the surface will not match the orbital period of the binary. And now there exist large samples of close binaries where we can look at where the orbital periods can be measured. That's the x-axis here, as well as the surface rotation period from something like spots. And you can construct a ratio of what the orbital period looks like relative to the surface rotation period. And what we find is those two things tend to be very close together. There seems to be very little difference between the rotation and the orbital periods in these tight binaries, which suggests that there's sort of minimal radial differential rotation in these stars. And given that that's consistent with the sun, we put that together into some sort of picture that says, well, the radial rotation profile is approximately a solid body. That there are strong mass trends in the rotation sequence. There's kind of subdominant metallicity trends. And we find that close binary stars tend to rotate faster, but that wide binary stars are not strongly affected in their rotation distribution. So I'm, again, going to pause for 30 seconds to see if there are any kind of clarifying questions before I go on.
We have a question from Joelson.
Go ahead.
Hi, Jamie. Yeah, I was just wondering about differential rotation on the surface in that sample. I mean, so for the sun, obviously there's differential rotation on the surface of the sun that you can't really probe with, well, you can probe, I guess, with the width of like a peak in your periodigram or something. Did you look into that in that work?
Yeah, so for the title for the binary work, we did actually put together, Adam Germain did a lot of work to put together a full model that can include both radial and latitudinal differential rotation simultaneously, constraints on both of them, right? There's some amount of trade-off and some amount of uncertainties, but actually that's part of the reason this is not actually a flat line at one here. We do fit some slight amount of latitudinal differential rotation on average in this sample, but it's not extremely well constrained. We think there probably exists some, but it's a little bit, I don't want to be too specific about exactly how much, but in doing that constraint, you can kind of put a joint constraint on the radial differential rotation, and that seems to be relatively small.
Got it. Thanks.
Great. Okay, so then you move kind of to the later main sequence in these stars, and you can put together a diagram like this where you're looking at the ages of the stars on the x-axis here and the rotation period on the y-axis. So this is sort of similar to that Skumanich 1972 plot where stars are slowing down over time on average. And if you look kind of at late phases past the mark of the sun here, right, there are a few stars where it looks like they're spinning relatively slowly compared to this line. That's probably related to stars that are starting to evolve off the main sequence, and so this sort of simplified drawing a line isn't really appropriate because the radii have started to change significantly. But you also see this interesting excess of stars that seem to be rotating faster than what these sort of simplified wind predictions would predict. And that has been an interesting avenue for a lot of study. And one of the suggestions from Jennifer Van Seters is that if you look at the rotation periods of these stars as a function of age and bin them in some sort of equivalent group, that at some point they start spinning much faster than they ought to if the loss is continuing in the same way. And her suggestion for this was that perhaps something about the magnetic field morphology, something about the breaking law itself, something about the angular momentum law, something about the wind is changing at some particular Rossby number that's close to the Rossby number of the sun. If you make that assumption, it says that then those stars probably, you don't necessarily need to change anything about the mass loss from those stars. You just need to change something about the magnetic field morphology. And you can end up with a prediction that the rotation periods basically stop slowing down, that those stars should retain more angular momentum than you otherwise would have expected. And you can make models for this. Now, you might argue, for example, that, detecting spots, detecting activity, detecting at large active regions are rare in slowly spinning stars. That's true. This is work from Zach Cleater, who I'm very excited is going to be a postdoc with me in the future. It's starting in the fall. But that at long periods, you are much less likely to detect a rotation period. So this caused many people to question, could this be a sample selection effect, depending on what sample was looked at, where you could detect rotation. The nice thing is that there are many different ways to measure the rotation. And so people like Oliver Hall have gone through and said, okay, well, we can measure an astroseismic estimate of the surface rotation rate, which does not have the same sample selection effects, does not have the same dependencies, can measure much slower rotation rates. And even in that sample, you see a pileup, you see a stalling of the angular momentum loss where stars evolving almost vertically on this plot over time hit some kind of threshold period that depends on temperature and kind of stall out. They stop spinning down. So even if they're older than this, they are still rotating relatively rapidly. And so this suggests that this is indeed some physical change in what the angular momentum loss law looks like, rather than some sample selection effect. And that means that we can make models that include this sort of truncated breaking and predict how the rotation period on the y-axis here, with fast on the top and slow on the bottom, is evolving should be evolving as stars move from the main sequence on the left of this plot to the subgiant branch and on to the red giant branch. And I've color-coded these predictions by stellar mass, so that you can kind of see how the mass dependence should look. And there should be a dependence on stellar mass, right? Because these more massive stars were rotating more rapidly to begin with. They had less time to slow down. They triggered this truncated braking at an earlier point, and so they have lost less angular momentum. And then you can kind of put the ensemble of data together, stars where we have rotation velocities, stars where we have rotation periods, stars where we have these seismic envelope rotation rates, all again color-coded by the masses of these stars inferred from astroseismology. And you can see that this makes a relatively reasonable match to what we are predicting in these models that include truncated braking, where kind of the orange points are following the orange line, the green points are following the green line, and so on. Interestingly, if you try and use models that don't include this truncated braking, you predict significantly more slowdown, especially for these kind of lower mass stars. And so your models start to be a little bit slow compared to what we actually observe in terms of surface rotation rates. And so that seems to suggest that, yes, indeed, this truncated braking is a reasonable way of understanding, at least empirically, what is happening in these stars. And so you can take these predictions of what the surface rotation evolution, and this is a regime where conveniently the astroseismology, the coupling between the modes in the core and the modes in the envelope is relatively strong. And so people can estimate a rotation periods for the cores of these stars, again, in the same way color-coded by mass. So you can compare kind of a red point of what the core is doing to the red line of what the surface should be doing. And you see that there is not a strong mass dependence in the core rotation data, but that it is very clearly different from what the surfaces of these stars are doing. It looks like as the cores contract, they spin up. That makes sense, but they don't spin up quite as much as you would expect if they weren't talking to their envelopes at all. And then at some point, they kind of flatline out or maybe start to decrease. Now, this is the data from Kepler. You can also add the data that we're starting to get from TESS, which kind of fills in this gap between the end of the main sequence and the early red giant stars, because we've targeted these subgiants specifically in TESS. And you can fill out kind of the evolution of the core rotation rate from kind of the subgiant branch out to the giant branch. And you can see there must be somewhere in the stars, very strong radial differential rotation between what the core is doing and what's happening at the surface. And you can sort of step from that to individually interesting cases. And this is a particularly interesting lower giant that we've started looking at recently, where we're looking at the predicted rotation frequency as a function of the radial mass coordinate. So the inside of the star is at the left side of this plot, the outside of the star is the right side of this plot. The model here is a prediction from the Fuller et al. Theory of what the internal rotation profile should look like. They put most of the radial differential rotation as happening right near the hydrogen burning shell, which is a reasonable place to put it. It's a hard place to measure. The interior to that, the star is contracting. Exterior to that, it's expanding. And so you get some prediction of what the radial rotation profile should look like in a star like this. And in this particular case, we see interesting differences from that. So on the left side of this plot, the seismic core rotation that's been measured is sort of roughly consistent with what the model is predicting. It's spinning much faster than what we think the surface should be doing. That's consistent with what the ensemble looks like. On the right side of this plot, we see in the envelope, there's a seismic envelope rotation rate. That's the green point. And that, again, is spinning a little bit faster than what this theory predicts. But again, it doesn't have all of the truncated braking and all of that folded in. So maybe that's okay. That's just some sort of scale shift in the average angular momentum. But what's interesting in this particular star is that pink point. That's a rotation velocity measured from a v sine I. And since we have the astroseismology, we can compute I and back it out into a rotation rate. And that is significantly faster than what the envelope is doing or what an ensemble would predict this star should be rotating at. So we suspect, perhaps, that something is pumping angular momentum into the surface of this star, likely some sort of tidal interaction with some other object nearby, is causing an interesting inversion in the radial rotation profile. Now, of course, this is one star, one unique object. It's interacting with something as it goes up in the giant branch, great, but what can you step from that to? And so Christine Mazzola-Lahire, who's going to start as a postdoc at OSU in the fall, has been looking at an ensemble of stars that are known to be in binaries. And so the x-axis here is the radial velocity variability of these stars. So basically, as they orbit each other, the star gets pulled towards and away from us. How much it gets pulled, the amount of radial velocity variability, should correspond to kind of the radius of the orbit as well as the mass ratio of the stars. And then on the y-axis here, we've measured the rotation velocities of these stars. And so if you believe in this tidal spin-up theory, right, as stars interact, there's some particular region of allowed space where stars get spun up to some rate given the orbital separation and its radius, the orbital separation and the mass ratio. And you can actually go and look at an ensemble of data where we have, these are kind of lower giant branch stars, so log G's between 2 and 3, where you're looking at the rotation velocities as a function of this radial velocity variability. And you can see that the ensemble actually matches this tidal circularization theory relatively well, right? These stars, there is a significant sample of stars that are rotating more rapidly than you would expect, so that's higher up on this plot, that have significant radial velocity variability from some sort of companion, so to the right on this plot. And those are almost certainly the stars that are currently or have recently interacted with something. And so you can start to see the effects of binarity directly. And so for kind of subgiants and red giants, what we see are mass-dependent surface rotation rates, which are inherited from the previous kind of main sequence evolution. The core rotation rates are interestingly mass-independent, and there are relatively minimal metallicity trends, except maybe the effects of binarity. But we see significant radial differential rotation, and we see binaries that can spin up the surfaces of the stars. And I'm going to jump, because I'm running out of time and I want the little bit of question time at the end, to talking a little bit about the core helium burning phase. So as these stars evolve up the red giant branch, right, their inert helium core is growing, it's getting hotter until they can start to ignite that helium burning. When that happens, they contract back down to a particular radius, a particular gravity, a particular luminosity that's set by that core size. And so that means if you look in a sample of stars where you say, as a function of the mass that I measure, as a function of the gravity, so evolving upward on this plot, you can see where you can actually measure surface rotation, which is the individual points of various shapes and colors, and then where your theoretical models predict that you should measure rotation. And what you'll notice, first off, is probably this excess of measurably rotating stars in these low mass regions where you don't expect to see a rotation, right? The sun is rotating at something like 2 kilometers per second. If you make it 10 times bigger, it slows down even more. You should not be able to detect that rotation. But all of these stars that were spun up in these tidal interactions as they went up the red giant branch, right, they've gained angular momentum. They haven't had time to dump all that angular momentum yet. And so they are now rapidly rotating in this core helium burning phase, which is part of how we get this number that 10 to 13% of stars should interact with something on the red giant branch. The other thing you can look at is sort of the intermediate mass stars, these 2 to 3 solar mass stars on the left half of the previous plot. So there, right, they started off rotating rapidly on the main sequence. They didn't have surface convection zones, so they couldn't drive significant angular momentum loss in that part of their evolution. And so it is only once they have started to evolve into subgiants and red giants that they've developed the surface convection zone and started triggering these same sort of winds. In kind of that old and simplified model, the amount of wind and angular momentum loss that they should have is relatively small, which means that we predict them to be rotating rapidly when they hit this core helium burning phase, sort of 10-ish kilometers per second. if you use these new, more sophisticated models of angular momentum loss that include things like an explicit mass dependence, radius dependence, luminosity dependence, photospheric pressure, convective overturn timescale, you predict significantly more loss in the stars, which move them much closer to the sorts of average rotation rates that we observe, sort of more like 3 or 5 kilometers per second than 10. And so we suspect that this is one of the ways where we can start to distinguish between different models of these losses and wins, because we're looking at a very different set of parameter space. This is also a region where the cores couple to the surfaces of these stars, and so you can measure using astroseismology the rotation period of the core as the star evolves in surface gravity. So that's from left to right on this plot. The envelope of this star is expanding. The core moment of inertia is not changing significantly. So the fact that these stars are slowing down over time in the core helium burning phase suggests that there must be angular momentum transport between the core and the envelope. Now you can look at this and you can compare this to kind of what you predict the surface rotation rates of these stars should be using these more sophisticated angular momentum loss models. And there's basically a factor of 2-ish difference between what we think the surfaces of these stars should be doing and what their cores are doing. Now you can look that for this particular sample, given what you predict for what the core rotation periods are, we don't see strong trends with mass in these core rotation periods. We don't see strong trends with metallicity in these core rotation periods. And this kind of core surface contrast, this factor of 2, is significantly less than what we saw in the red giant branch, the shell hydrogen burning phase. It's also not very large, which means that you could just differentially rotate the envelope of the star, that's what the pink bar is here is, and you would sufficiently differentially rotate the entire, you could adequately get a similar contrast that you see between the surface and the core. Now, that's not saying there is not differential rotation in the radial regions of the star, so the interior of the star. This is just saying that if you differentially rotate the envelope, it can be no stronger than sort of omega goes as r to the -1 to match what we see empirically, and is likely a little bit smaller than that. So in the core helium burning phase, we see surface rotation rates that are somewhat mass dependent just from the inherited loss. We see core rotation has a minimal mass dependence and minimal metallicity dependence. There's less differential rotation than what we saw in the first ascent red giant branch. So these stars have, over the course of their lifetime, decoupled, recoupled, decoupled, recoupled, and then probably at the end in the AGB phase, decouple again. And then these binaries are spinning up the surfaces of these stars in a very measurable way. So I'm going to stop there, leave out my conclusions. Hopefully I've convinced you that we have empirical data on the evolution of stellar rotation all the way from the pre-main sequence to the post-main sequence, that binaries are not a negligible part, and that this empirical evolution is telling us a lot about the physics of magnetism, rotation, angular momentum loss, winds, angular momentum transport in the interior, as well as the effects and distribution of binaries and tides. So thank you so much for having me, and I'll be happy to take any questions.
Thank you, Jamie, for a very nice and comprehensive walkthrough. You see several people clapping. I clap for the audience. And I would like to open the floor for questions. We have the tradition that the first questions are asked by students, and so I would like to invite them. Please indicate with the raised hand if you have a question, or put your question into the chat. The first question is by Phil. Please go ahead.
Hello. I have a question about something that you mentioned during the first section where you talked about astroseismology. You mentioned something that was called, I think, Zeeman splitting.
Mm-hmm.
Yeah. What is that? I never heard that mentioned before.
Yeah, so Zeeman splitting isn't actually an astroseismic thing. It's actually when you have a strong magnetic field and you're looking at a spectral line, the magnetism slightly changes the energy levels of something like a hydrogen atom. or any atom that has a magnetic dipole moment, I believe. And that gives you a splitting, basically a differentiation between kind of different energy levels of different spins. And it's kind of an analogous process because it will change a spectral line to have multiple peaks in kind of the same way that a Doppler splitting will cause you to have things coming towards you or things coming away from you. So when I try to explain the splitting in astroseismology, which is sort of a little bit harder to wrap one's head around physically, I try to draw an analogy between either like a Doppler-like effect where you're shifting the frequencies higher or lower, or a Zeeman effect where you would be sending kind of the wave, splitting the wavelengths higher and lower. So it's more of an analogy. It's not actually related to the physics that's happening here. It's more related to the physics of magnetism. Yeah.
Okay, thank you.
Next one is Lucas. Lucas?
Hear me?
Okay, now we hear you.
Okay, thanks. So first of all, thanks for the nice talk. I actually have two questions. One is more of understanding thing. You showed this Rossby number plot, and there was like a dashed line. What exactly is this dash? Does this dashed line mean? Is it some kind of statistical measure, or?
Oh gosh, which Rossby number plot?
It was like a histogram or two histograms.
Yes, yeah, exactly.
There was like some dashed line, and I couldn't wrap my head around what this actually meant.
I believe the dashed line here is about the Rossby number of the sun, and I'm not sure if this is after Jen's paper, so it may be exactly the line that they used for the where you stop detecting, where this truncated breaking sets in, or it could be the Rossby number of the sun. I don't know exactly what scale it's on here, but it's that approximately. So it's just kind of to give you a sense of, related to kind of what we've been talking about previously, the fast rotating things tend to be more detectable, more active in spots, whereas kind of more slowly rotating things are not.
Okay, that makes sense. And the second thing is, I think you mentioned about closed binaries, that closed systems are spinning up the surface even more. Mm-hmm. Is this due to mass transfer, or what is the physics behind?
So there are almost certainly cases where mass transfer is involved, but even before you get close enough to do mass transfer, you feel the effects of tides. And so depending on the relationship between the orbital periods and the initial rotation periods, you will feel tidal drag forces that either spin you up or slow you down. And in most cases for stars like this, it's spin you up. Because the orbit has so basically you're transferring angular momentum from the orbit into the spin of the star, and so the orbit tends to get a little bit tighter over time and the spin tends to increase.
Okay, I think it makes sense.
Great,
thanks.
So before I give the stage back to Philip, please just indicate if you have any questions, and after the question of Philip, we would also have senior people having questions. So please simply indicate if you want to contribute. Phil?
I have more of a follow-up question. So the spin up for closed binaries, that's part of the tidal synchronization of the system.
Yes. Yes.
Thank you.
Yeah, exactly. You're moving your way towards tidal synchronization, but that's a process that has a time scale.
Yeah. Okay. Other people? If you have any questions, I see. Well, so okay. Well, then I keep my questions for later. Savita, please go ahead.
Yes. Hi, Jamie. Thanks for the very comprehensive talk with the whole evolution on from the pre-main sequence to the Rajas. It's very, very good. So one thing that you mentioned, and I was I've been thinking a lot about this, but maybe you have some answer about this, was you were talking about the evolution of you starting with the decoupling, coupling, decoupling. I mean, all this coupling, decoupling that's happening, but every time I guess there's a different reason why it's happening, but do we actually know exactly why?
No, this
Different
is
phases.
the question, the very deep question of like what physical process is transferring the angular momentum between the core and the envelope, right? Because decoupling and recoupling is kind of a simplification, right? There's almost certainly transport happening at all times. The question is the transport time scale faster or slower than the evolutionary time scale in that phase? And what is driving that transport time scale? And, this is a case where people are like, well, magnetism may be important in some regimes. Internal gravity waves may be important in some regimes. Hydrodynamic mechanisms and shears may be important in some regimes. But figuring out what process is dominating in what regime is something that I don't think we've done a great job of yet. And what I'm hoping is that we have enough empirical data to say it's not this, it's not this, it's not this in this regime for stars of this mass in this particular evolutionary phase. But so far, I think we've ruled out too many things. And so nothing quite works, which suggests there's either some processes we don't know about, or there's some interactions between the various physical processes left to be discovered and worked through.
Okay, thanks.
Yeah, but the overall thing I found so far is that core burning phases tend to be more strongly coupled, and shell burning phases seem to be less strongly coupled.
Okay.
And how does this compare along the shell burning phase? Is there also a gradient?
Yes, right. That's the red giant models, right? As you're going through kind of the red giant phase, right? You're increasing, you're going through the shell burning phase. I would argue that the surfaces are spinning down more, and therefore there is the gradient is increasing even if the rotation period of the core is not changing. But that relies on an inference which is based in conservation of angular momentum, so I think is a relatively reasonable one. But measuring those surface rotation periods for these very slowly rotating stars, hundreds, 200s, thousands of days, is extremely challenging. And so it's very hard to get direct evidence. And it is rare that we have even kind of the 3-point rotation profile that I showed for the star that I think might be spinning up tidally. And so when you have 2 points, it's very hard to say where in that regime is the differential rotation happening. Are there multiple zones of radial differential rotation? Are they increasing smoothly or choppily? There's a lot of physics I don't think we understand.
And how much is it limiting? Because with mixed modes, we only can probe basically the lower part of the RGB. How much does it hurt the modeling that we don't know the more luminous? And okay, and then I have another question. Go on.
Yeah. No, so I think I have assumed that the upper RGB looks the same as the lower RGB. So basically the cores are rotating at basically fixed period and the surfaces are continuing it to expand and slow down. There is no way to check that except to say that it's not inconsistent with what we see in the core helium burning phase to kind of run the models that way. But given that, especially in stars where you have a helium flash, there's a lot of physics that we really don't understand about that. There could be mixing, there could be angular momentum transport in that regime. Plus, you have all the effects of binaries that have very large separations, which are now interacting with. So actually drawing that consensus is extremely challenging. And so I have been assuming that the fact that we can't measure that is not a problem, but there's no way to, it is very hard to disprove that assumption. And it would be great if it was possible to make those measurements, but my impression is not.
Well, the mixed modes are simply too squashed that we can even separate them. And the other thing is, on the luminous RGB, we should have substantial amount of mass loss. And we always see what it takes on the main sequence. It's slowing down the sun. Is that being taken into account in the models to slow? Oh.
Yeah, so interestingly, so we can actually, depending on how well you believe the evolutionary state dependence of our astroseismic masses, which I think are getting better now, you can actually look at the RGB stars versus the red clump stars in something like the Apogee Kepler catalog and actually empirically look up what the mass loss looks like. And it is consistent with previous astroseismic investigations of open cluster stars, which is that at high metallicity close to solar metallicity, the amount of mass loss on the RGB is actually not as large as people originally thought. It's kind of less than 1/10 of a solar mass, which is still significant. I don't know how well, right? You have to think about that phase of evolution is relatively fast. The rotation is relatively slow, so you don't get that same boost in the amount of angular momentum carried away by a fixed amount of mass that you would in a faster rotating regime. And so I so far have argued that it's not a deeply important uncertainty in what we're trying to do here, but it's definitely something worth considering. And as we move towards lower metallicities where it looks like there's significantly more mass loss, it's something we want to think about a lot harder, I would say.
Okay, and this is where the expected trend with metallicity comes from. Is that correct, or
that's not, so that's the ones I've showed as a function of metallicity. I haven't deeply included the mass loss because those are mostly the more massive stars, which don't get as luminous and therefore don't go up to the same tip values, and we expect them to lose less mass. And so I don't think that's more frozen in from the main sequence and from the distribution of binarity, although I am not going to argue that those models can't be revised and improved, but I think it's not the dominant uncertainty yet.
Okay. So with this, I would be happy to invite people as well joining the discussion. Okay, so I think there is no more content. I don't even want to open our discussion on binaries because that might go for hours and days. So because I haven't seen the paper, it is very interesting, and we all have targets. We should look into that. So with this, I would like to thank Jamie again for speaking here today. It was a pleasure, and I will stop the recording.